Whenever you study quantum mechanics, you will be introduced to two distinct mathematical formulations or models of the quantum mechanical theory. Usually, initially students are quite familiar with the Schrödinger equation, which is written as a differential equation. So whenever you are dealing with a differential equation, you know how to solve differential equations. The solution is a wave function solution that gives you some idea about probability densities, expectation values, etc., etc. But maybe at a later stage in time, you will be introduced the matrix eigenvalue problem. And I have seen that certain students face difficulty when they are transitioning from the Schrödinger's wave mechanical formulation to the Heisenberg's matrix mechanical formulation. But the good news is both these two mathematical formulations are physically equivalent. They make equivalent predictions. So they are essentially the same physical theory. It's just that the mathematical representation is slightly different. And once you understand the reasoning behind this and the distinction in the mathematical representation, both these two formulations will be very, very easy for you. Hi, I am Divya. This is For the Love of Physics, and in this video I want to present to you the matrix representation of quantum mechanical theory. I have produced a large number of lectures till now in the quantum mechanics lecture series, where I have mostly focused on the Schrödinger's wave mechanical formulation, where we have been dealing with the differential equation, its solution, which is the wave function solution. This kind of a mathematical model is very suitable whenever we are dealing with systems with a continuous basis. For example, the description of a wave function in position basis. So for example, we did problems on infinite potential well, finite potential well, step potential, etc., quantum tunneling. Those all problems were solved using the differential equation approach, right? But now in my advanced quantum mechanics lecture series, I want to take this a step forward, because I have already described to you what is a ket, what is a bra, what is a Hilbert operator, what is the operator formalism of quantum mechanics. The time has finally come for us to look at the Heisenberg's matrix mechanical formulation, which was essentially given by Heisenberg and other scientists. Here, the fundamental equation is written not in the form of a differential equation, but in the form of a matrix equation. And if you are familiar with matrices, this is no different from this particular formulation. It's just that the mathematics is slightly different, and that is what we want to understand today. This kind of a formulation has its own advantages, especially when we are dealing with systems with discrete basis. So for example, we are going to be talking about systems like harmonic oscillator, the operator formalism of harmonic oscillator using ladder operator approach, and later on we are also going to study angular momentum, spin angular momentum systems, etc. There, this kind of a mathematical formulation is quite helpful for studying a given system. Now remember my lectures on Kets, bras and Hilbert spaces, where I said that a quantum state which can be described as a ket vector or a state vector is essentially an abstract vector in Hilbert space. And just like we have vectors in Euclidean spaces, where the vectors can be written in a certain manner, the vectors experience certain kinds of mathematical operations. Similarly, these kinds of quantum states which belong to an abstract Hilbert spaces can also be represented in a very much similar manner, which actually is not really that difficult if you spend a little bit of time understanding the representation here. So first I want to give you a matrix representation of Kets and bra vectors. So if you have any kind of a difficulty here, just keep in mind that the quantum state or the ket vector is represented as an abstract vector in Hilbert space, just like a geometrical vector is represented in a Euclidean space. So for example, if I have any kind of a quantum system where the basis of that quantum system can be described as a complete orthonormal basis, discrete, complete and orthonormal basis, and we call this basis as phi phi n. Okay, the curly bracket represents that there are an n number of basis vectors in this particular space. So for example, we may have phi 1, phi 2, phi 3, phi n. It might be a finite basis or it could be an infinite basis, doesn't matter. So the basis simply means that these are the unit vectors in that given space. These are orthonormal. So if I take an inner product between two distinct basis vectors, the answer will come out to be 0. And if in this kind of a system we try to represent a quantum state, that quantum state is, let's suppose, psi. Now you know that the psi can be represented simply as a linear sum of these basis vectors. So for example, a1 phi 1 plus a2 phi 2 and on. So this is nothing but a summation over an phi n, where n goes from, let's suppose, n is equal to 1 to infinity for an infinite dimensional space. Now this kind of a description is no different from the description of a geometrical vector in Euclidean space, where in an Euclidean space a geometrical vector can be written in terms of 3 distinct components, and all these 3 distinct components are essentially nothing but the projection of that particular vector with respect to the unit axes or the unit directions I cap, j cap and k cap. So which means that even here in this case we can write these coefficients an as simply nothing but the projection of the state vector onto these individual basis vectors. So if I have phi n and psi, then this is going to give me the coefficients involved. I mean, you can check it for yourself. So for example, if I just substitute this expression here, I'll simply end up getting a1 phi n phi 1 plus a2 phi n phi 2 plus on and on. So all these terms will be 0, and only that particular term where phi n inner product phi n comes will survive, and therefore the an corresponding to that inner product will survive. You see this? So this can be written in the form of the basis vectors of a system, where these kinds of coefficients are simply nothing but the projection of that particular state vector onto the basis vectors here. Therefore, one simple way of representing this kind of a quantum state is, so if I have state psi, I can simply represent this quantum state as a column vector using these coefficients, all right, with respect to the given basis, of course. So if I have a column vector like this, where I will write a1, a2, a3 and on, then with respect to this given basis, this is a perfectly valid representation of the state vector in this particular space. And if this is the state vector which is written as a column vector, then the bra corresponding to this, and you guys are familiar with what the bra is, right? So the bra is essentially this, which is nothing but the Hermitian adjoint of its ket, right? Of its ket. So what does this give us? It simply gives us a row vector containing the elements which are the complex conjugates of a1, a2, a3, a4, like that. So this is nothing but a1 star, a2 star, a3 star and on. So this is the representation of a ket vector and the bra vector, which is defined in a space containing these basis vectors. All right. And the moment we define them in this particular manner, various other operations quite simply follow in a very simple manner. So for example, if I want to describe the inner product, right? So for example, the inner product between psi and psi itself, let's suppose. I could have taken a different state as well, but I think the idea is easily understood from here. Then this is simply nothing but a1 star, a2 star, a3 star. This is the bra vector, and this is a1, a2, a3. This is the ket vector, which is nothing but the summation of an star an from n is equal to 1 to infinity. And this is simply for the self inner product an mod square. So this is a very unique representation of a given quantum mechanical state with respect to a set of basis vectors in terms of column and row matrices, which I think you will be able to absorb or understand much better if you think of it in the similar fashion the way you think of geometrical vectors in Euclidean space, because there we do this kind of a representation also. Now think of that same geometrical vector. What if we perform some operation on that geometrical vector? For example, if we perform an operation of translation or rotation or scaling or inversion, then those kinds of operations or transformations can be represented by matrices. And we can do the same thing here in our sort of a matrix representation where we have quantum states belonging to Hilbert space. All the various operators, whether it's Hamiltonian operator, angular momentum operator, etc., can be represented as square matrices acting on these column vectors. So let me just show you how we can do that. Let's first rub the board. So let's suppose that we have an operator corresponding to some kind of an observable, and we are going to call that observable A. So the operator I'm going to call as A hat. And let's suppose A hat acts on the quantum state psi. Now the quantum state psi is written as a linear superposition of all the basis vectors. So this is quite simply put summation of an phi n over n. All right. Now, before we can figure out what is the nature of this operator, we must try to look at what happens when this operator acts on the basis vectors themselves. So what if some kind of an operator acts on the axes of a given coordinate system? Let's suppose we talk about rotation. If we talk about rotation, then the new axes can be represented in terms of the old axes, right? If I rotate a coordinate system, the new axes can be written in terms of the old axes themselves. So if I want to look at the action of A hat on each of the basis vectors, so let's suppose I have phi 1 here, then the action can be represented as a new vector which can be represented in terms of the old basis vectors themselves. So let's say that I call this as A11 phi 1 plus A21 phi 2 plus A31 phi 3 and on. So here these are all the basis vectors and these are the components associated with the basis vectors after the transformation, after this operator has acted on this particular system. By the way, I need to tell you that in quantum mechanics, the operators that I'm describing here essentially represent linear transformations. You know, linear transformation follows that when we have this particular property of a linear transformation. Let me just write here, if you guys forgot, I have talked about linear transformations before when I was talking about Hermitian operators, etc. So linear transformation means if you have any kind of a operator and you operate this onto some kind of a state psi 1 plus psi 2. Okay, I could as well as take some coefficients here, but it's okay. I just want to convey the idea. So if the linear transformation acts on the sum of psi 1 and psi 2, then this simply means that this is nothing but the sum of the operator acting on some psi 1 and the operator acting on psi 2. That's it. So being a linear transformation, it satisfies this particular property. So because of this reason, the action of A hat on phi 1 can be written in this manner, and similarly the action of A hat on phi 2 can be written as A, this is 1 2 acting on phi 1 plus A 2 2 acting on phi 2 plus A 3 2 acting on phi 3 and on and on. Okay, it could be a finite dimensional as well as an infinite dimensional space. So accordingly, we will have that many number of terms. A hat acting on phi 3. So A, this is going to be equal to 1 3 phi 1 plus A 2 3 phi 2 plus A 3 3 phi 3 and on. Similarly, you will have a large number of terms depending upon the nature of the system. So you can have something like A acting on phi n is equal to A 1n acting on phi 1, 2n acting on phi 2, 3n acting on phi 3. So you can see that the linear transformation corresponding to this kind of an operator A hat in the quantum mechanical system can be represented in this particular manner if the operator acts on the basis vectors themselves. Now, once we understand how the operator behaves when it acts on the basis vectors, only then we can represent the operator acting on psi in a specific manner, because this entire operation can be written in a very compact manner. Okay, so A acting on phi n can be represented as a linear sum over M, where we have a mn acting on phi m. So n subscript here corresponds to this particular subscript on the left hand side, and m subscript here corresponds to all these subscripts going from 1 up to whatever is the dimension of the system over and summation on top of it. So this is the compact manner of how the operation of A acts on the basis vectors. Now if I take an inner product, let's suppose if I take an inner product of some random phi m with the left hand side, okay, m could be anything here, then if phi m goes here, then this is simply represented as m a mn, and here you have phi m. Of course, only those terms will survive where out of this summation the particular term corresponding to the value of m, therefore this comes out to be equal to 1, and I will end up getting the terms mn. So essentially the way we represent a operator in quantum mechanics with respect to basis vectors is we construct a square matrix corresponding to these particular terms. So if I can construct a square matrix associated with these particular terms, and that square matrix acts on a given state, then I will end up getting something which is similar to a matrix multiplication operation. So for example, now if I want to look at what happens if A acts on the state psi, right? If A acts on the state psi, then that is quite simply put as A acting on summation over n an phi n, right? But we already know what happens when A acts on phi n. We end up getting this. So therefore, this is nothing but a summation over, so the operator acts on the phi n, and if it acts on phi n, I will get the summation over n and the summation over m a mn an phi m. All right. And this is not very difficult to understand if you sort of notice that when a operation is performed on a state, we essentially get some kind of a new state. Let's suppose we call this as psi dash. Okay, when an operation is performed on a state, we get a new state. But because these states are represented as column vectors using the components or the projections of the vector onto the basis states, so therefore this would probably be written as a summation over some an dash phi n, right? Right. So psi is written as a linear superposition of the basis vectors having some kind of a projections an. When we perform certain operation onto psi, it transforms and we end up getting a new vector which can be written as a linear superposition of the same basis vectors, but the projections are different. Essentially what this means is that if I compare this with this, I think I should write m here just for the sake of making sense of it. Here am dash is nothing but amnen. That's it. So the column vector, which is the result of the operation of A on psi, is nothing but this particular square matrix corresponding to this operation acting on the column vector corresponding to psi itself. Now this is very much similar to an example that I want to provide in vector space. So you guys are familiar with the geometrical vectors in 3D or 2D coordinate systems. What if I perform an operation of rotation? Right? If I perform an operation of rotation, I essentially rotate the vector, let's suppose, by 60 degrees. That same operation can be represented mathematically as the final vector is equal to the rotation matrix operating on to the initial vector. That's it. That is all. So when we perform the rotation matrix operation onto the initial vector, I end up getting the final vector. So this kind of an idea is now applied in the abstract Hilbert space where we are dealing with quantum state vectors, that's all. So whenever we want to perform some operation onto a state, it essentially means that we are performing some kind of a matrix multiplication of a matrix associated with the operator onto that particular state, which is written as a column vector. This will give us the final quantum mechanical state that we obtain after the operation. So essentially, this kind of an operator corresponding to a given set of bases has a matrix representation which is quite easy to understand. So if this is the way that the operator transforms the basis vectors, then I can represent the matrix A as a square matrix containing all these components. So you have a 1 1, a 1 2, a 1 3, a 2 1, a 2 2, a 2 3, a 3 1, a 3 2, a 3 3, and on and on. This is the square matrix representation of an operator in a given quantum mechanical system. And you know how we can obtain all these terms here? We can obtain all these terms from this particular expression. So all these terms, I should say, AMN is nothing but the inner product of phi m, a hat, phi n. That's it. So if I want to represent this square matrix in terms of these products, this is quite simply put. The first term will be, of course, phi 1 a hat phi 1 in a product. The second term will be phi 1 a hat phi 2, and on. Similarly, the second row will be phi 2 a hat phi 1, then phi 2 a hat phi 2, and on. Third row, phi 3 a hat phi 1, then we have phi 3 a hat phi 2, and on. We will get the entire set of rows and columns. You see this? This is the way we can represent any operator in the matrix formulation of quantum mechanics as a square matrix, where the various terms of the square matrix can be obtained by simply studying the effect of the operator onto the basis vectors themselves. So this is the representation of the operator with respect to the basis vectors of the given quantum mechanical system. So now when you understand how the quantum states are written as column vectors in Hilbert space, and the linear transformations or the operations on those quantum states are represented as square matrices, where the components or the terms are simply obtained by the inner product of the operation squeezed between the various combinations of the basis vectors. Now, the Schrodinger equation can be written in a much simpler manner that simply involves matrix equations. And if you are familiar with matrix equations, you can perform different kinds of quantum mechanical operations with it. But to give you a much more clearer picture, I want to do a couple of problem solving. So I have two distinct problems where we have questions related to energy eigenvalues, etc. And I want to use this newly sort of presented matrix representation for the performing of those kinds of questions. So if you stick with me and try to figure out the sort of problem solving that I'm going to present to you, then this kind of a representation will make much more sense in terms of the applicability in different kinds of problems. So if you want to take a snapshot, you can take a snapshot of the screen. I'm going to rub this board right now. So you can see a question on the screen. Let's suppose that there is a quantum system with three energy eigenvalues E1, E2 and E3. With respect to an orthonormal basis, construct the Hamiltonian operator as a matrix. All right. So this is not really that difficult a question. So they are giving you that with respect to an orthonormal basis, phi1, phi2 and phi3, you have the energy eigenvalues, and the energy eigenvalues are E1, E2 and E3. Since this is an orthonormal basis and the energy eigenvalues are E1, E2, E3, then what happens when the Hamiltonian acts on these quantum vectors? So Hamiltonian acts on phi1. Because these are the eigenvalues, I should get E1 phi1, right? When the Hamiltonian acts on phi2, I should get E2 phi2. When the Hamiltonian acts on phi3, I should get E3 phi3. All right. So this much is given in the question. Now the question is asking, how can we obtain the square matrix corresponding to this particular Hamiltonian? Students who are familiar with the matrix mechanics will instantly know the answer to this question. So if you are one of those students, then you can skip ahead to the next problem. But if you are a beginner level student, this is actually a very easy question because they have already given us the energy eigenvalues corresponding to a discrete orthonormal basis. So if I want to construct the matrix associated with the Hamiltonian, then the matrix is quite simply put. We have H11, H12, H21, H22, H23, H31, H32, H33, right? Now, how do we obtain these terms? These terms can simply be obtained by finding the inner product of the Hamiltonian with respect to, so for the 1 term, you have phi1 h hat phi1. For the 1-2 term, you have phi1 h hat phi2. For the 1-3 term, you have phi1 h hat phi3. Similarly, the other terms are phi2 h hat phi1, phi2 h hat phi2, phi2 h hat phi3, and the third row is kind of obvious. All right, so these are the terms that we need to evaluate. Now, because we are dealing with an orthonormal basis, these terms are not really that difficult to evaluate. So, if I look at, let's suppose, phi1, H acting on phi1. What happens when H Hamiltonian acts on phi1? You end up getting E1 phi1, where E1 is a constant. E1 is a constant, so constant can be taken out of the inner product. So, therefore, this comes out to be E1 phi1 inner product. An orthonormal basis, phi1 inner product with phi1 is nothing but 1, so this is just E1. So here I end up getting E1. All right, first term. What about the second term? Phi1 H acting on Phi2. Again, H acting on Phi2 will give us E2. So E2 is a constant, can be taken out. Phi1 inner product with Phi2. Because we're dealing with orthonormal basis, so if I take a dot product of I cap vector and j cap vector, it will come out to be 0. You know that, right? So the same thing is happening here. We're dealing with orthogonal vectors. So this will be 0. So this is nothing but 0. So this term is 0. For the third term, Phi1 Hamiltonian acting on Phi3. So this is Phi3, Phi1, Phi3, where this is 0. So therefore you end up getting 0 here. See? So we can repeat the calculations, but now I think it's kind of obvious. So if Hamiltonian acts on Phi1, we get E1, Phi1. Inner product of Phi1, Phi2 and Phi1 is 0, so we get 0 here. Hamiltonian acting on Phi2, we get E2. And the inner product of Phi2 with Phi2 is 1, so we get E2 here. Hamiltonian acting on Phi3 is E3, and the inner product of Phi2 and Phi3 is 0, so we get 0 here. Hamiltonian acting on Phi1 is E1, inner product of Phi3 and Phi1 is 0, so we get 0. Same goes for this term. And for the last term, we get Hamiltonian acting on Phi3, E3, and inner product of Phi3 and Phi3 is 1, so E3. Okay. So this is the matrix representation of the Hamiltonian operator for this quantum mechanical system. It's a very simple, very easy question. Now this next question is from a popular physics examination in India, JEST Physics 2015, and yeah, I would ask you guys to pause the video and try to solve this question yourself. That if a Hamiltonian H is given in this manner, where 0 ket and 1 ket are orthonormal states, then find the eigenvalues of this Hamiltonian. Now here the Hamiltonian is represented as an outer product of the various orthonormal state vectors. Outer product is not a scalar quantity. The outer product is in fact an operator. So the inner product represents a scalar quantity, but the outer product of two kets will represent a operator. So if I want to, so they are asking us to find the eigenvalues associated with this Hamiltonian corresponding to this orthonormal basis. Again, if you guys are familiar with the matrix representation, please pause the video, try to solve this question yourself, and then cross-check your answer with mine, okay? Because I'm going to follow the similar strategy here of obtaining the terms corresponding to the Hamiltonian matrix first. So here, I want to obtain H11. H11 is, so I can either call this 1, 1 or I can either call this 0, 1. So for example, we have the Hamiltonian matrix here, right? So I want to obtain the Hamiltonian matrix. So the Hamiltonian matrix H is given as, let's suppose, so here I can call this as H11, H12, H21, H22. I mean, you could also call it as H01, H0, H00, H01, H10, H11, right? I mean, it's up to you, as long as you understand that what they actually mean. So I'm going to, okay, let me keep this subscript in this particular manner here, while the orthonormal basis is 0 ket 1. So H11 is essentially nothing but 0 Hamiltonian 0 like this. So if I act this inner product onto this operator, I should end up getting 0, 0, 0, 0, minus 0, 1, and 1, 0, plus iota 0, 0, 1, 0, minus iota 1, minus iota 0, 1, and 0, 0. So because of the orthonormality, many of the terms will go to 0. This will go to 0, this will go to 0, this will go to 0. The only thing that you will have left is essentially this particular term, which is equal to nothing but 1. If I check the same thing for H12, H21 and H22, I should get in this particular manner, where this term will go to 0 and how many terms are there? 1, 2, 3, 4. 1, 2, 3, 4, and this term will go to 0 and this term will go to 0, and you are left with this particular term, which is nothing but iota, right? Same way this will give us 1, 0, 0, 0 minus 1, 1, 1, 0 plus iota 1, 0, 1, 0 inner product minus iota 1, 1, 0, 0 inner product. Again, all these terms will vanish and only this term will remain, which is minus iota. Okay, and the last term is 1 Hamiltonian 1. Okay, so this is 1, 0, 0, 1 minus 1, 1, 1, 1 plus iota 1, 0, 1, 1 minus iota 1, 1, 0, 1. So here this goes to 0, this goes to 0, this goes to 0, and you're left with minus 1. Therefore, the matrix finally comes out to be equal to 1 iota and minus iota minus 1. So this is the matrix associated with the given Hamiltonian operator corresponding to 0 ket and 1 ket orthonormal basis. But I want to find out the eigenvalues because that is what the question is asking. And the way to find eigenvalues is the same way you find eigenvalues in matrices. So if you are familiar with matrices, the way you find eigenvalues of a matrix is you write down the characteristic equation, take the determinant equal to 0, and the roots will give you the eigenvalues for that matrix. So that's it. So if I take the Hamiltonian matrix minus lambda I, characteristic equation determinant equal to 0, that should give us the result. So what is this? This is nothing but H is equal to 1 minus lambda iota minus iota minus iota minus lambda is equal to 0. That is nothing but 1 minus lambda, and then you have minus 1 plus lambda, and then you have minus minus plus iota square is equal to 0, which gives us, you have lambda plus 1, lambda minus 1. So therefore this is equal to minus 1 minus lambda square minus 1 is equal to 0, which is nothing but 1 minus lambda square is equal to minus 1, which means that lambda square is equal to 2 or lambda is equal to plus minus root 2. So these are the eigenvalues associated with this kind of a Hamiltonian operator corresponding to the given orthonormal basis, and to obtain them we do the same kind of a mathematical operation of finding out the eigenvalues of a given matrix, where we take the matrix corresponding to this operator. So that is all for today. I hope you have got an idea of how we can represent the quantum mechanical operation as well as the wave function state in terms of matrices. And if you are familiar with various matrix operations, we can perform these kinds of representations in the future in different kinds of problems. So in the future we're going to be talking about harmonic oscillator, operator formalism, angular momentum, spin angular momentum, where we will heavily rely on the matrix representation of quantum mechanics. So I'm Divya Jyotidas, this is For the Love of Physics. Thank you so much. I'll see you next time. Take care. Bye-bye.